So heading over to course materials and to our assignment Maya files, the assignment you're going to need today is this one right here, Anim1 tail ball. So just copy that and put it on your desktop or whatever space you're comfortable working. Just don't work directly off of the network. Go File, Open, and I'm going to open up the tail ball there. Now, this assignment, back here, head over to week 4, tail ball. There's a little bit of stuff I want to talk a little bit about, do a little bit of a demo before we kind of jump into the Maya itself. There's some examples I want us to have a look at. So I'm going to show a clip from a Disney film. So this is from Disney's Sword in the Stone, one of their classics from, I think, 1962 or 63. So what I want you to pay attention to is this squirrel, the way that it's moving. And what I want you to really focus on is try to imagine, rather than the entire squirrel, but imagine this being just a sphere, just a ball, and just a line. And that's what we're going to be looking at in terms of how to break down this, this assignment. So it's incredibly charming, and hopefully once you start watching this, you forget exactly what I told you to do, which is to look at the hip and pretend it's a sphere, and you just follow the characters. So you might be wondering, well, then what's the point of worrying about the tail? Well, what you look at is the way that the tail is behaving introduces some new animation principles. So we'll just have a look at this one. So one of the principles that we're looking at, right, we've been looking at are arcs, spacing, timing. This is sort of the beginning, right? These are the three most important. I call this sort of the Bermuda Triangle of animation. This is the first core of principles that you work with and try to understand: arcs, timing, and spacing. Then things get a little bit more complex, because when we start working with are things that are connected, right? So we have one object, a cube, right? A sphere. Those objects aren't connected to one another. They're individual, they're blocks. They're not that flexible, right? The most we can do is squash and stretch. But when you're looking at the hip, hopefully what you can see is, what's this? A squash and stretch, right? And the better analogy when you're talking about anatomy, right, is compression and extension. So yes, sometimes there are examples that you can look at that are that simplistic. But what's really important to understand is that muscles change shape because parts of the muscle contract and other parts will relax. So when you're looking at this from a drawing point of view, we're always paying attention to the model when we're looking at a pose and how the weight is distributed, where there's tension, and how that affects the shapes of muscles. So the same thing, we're looking at anatomy, right? We look at squash and stretch as compression and extension. But here it's pretty easy to see a one-to-one correlation. There's the ball, right? There's the sphere, there's the squash, and there's the stretch. But of course, what we've also got going on here is there's another object, right? So this is connected here, right? So here we have basically a shape, right? Kind of like a pear, right? And here the pear is really skinny, right? And here it's really fat, right? And kind of scrunched up, squashed over here. So we got that change going on. Now, the tail itself involves a different principle, and this is usually called overlapping action. Another principle is drag. Another one is called follow through. So follow through, drag, overlapping action. These are all principles that have to deal when you have connections and flexibility. Sorry, my tablet's acting a little flaky there. So when you have connections between objects, right, these principles, drag, overlap, and follow through, your animator's talking about those principles. So that basically, this is all animation code for physics. And we've already learned these as school kids, right? a body in motion tends to what? Stay in motion. So these are the basic laws of motion, right? So we all learned this as school kids. Now it's time to put it to practice, okay? Not with equations, but with an understanding. And we all do this. Anybody play sports, right? Anybody kick a soccer ball? You see how some people can kick a soccer ball so accurately, it lands right on the toe of their buddy downhill, right? That's physics, right? But it's an intuitive understanding. So a body in motion tends to stay in motion unless another force acts on it. So the same thing with the tail, okay? So the tail is here, right? And I can see, well, what is the force, right? The hip is applying force and I'm going this way, right? So the hip is going up. What way is the tail going? What direction is it pointed? Down, okay? So this is another principle, right? So all matter will resist movement as much as possible until a force stronger than it overcomes it, whether that be friction, right? Air resistance, a collision. But this is something that you can observe, right? So when you grab an object, let's say I grab my pen, right? If I hold it very, very strong and then move my wrist, it's not very flexible. But if I hold it loose, it behaves differently. So the way something moves tells you about how flexible the connection is. If this wasn't a tail, if I took like a solid piece of wood and just nailed it to the back of this squirrel, right, with a little thumbtack, it would not behave the same way as a tail with dozens and dozens of vertebrae in there that can all flex and move, right? It'll behave differently. So what we're trying to get a handle on is, well, okay, how do we look at flexibility and how do we create that, right? Where does that illusion come from? And usually you start with something very simple. If I could understand this, instead of it being all these little connections with really complicated shapes, if I could restrict this to something very simple, like a block, would it make as much sense? So that means that when the character is going up, then this is going to resist. It resists because it has weight. And if the only flexible part is here, I pull up, this rotates down. So drag is always against the main or primary force. Okay, and it's very easy to observe. If you are very relaxed in your head and neck and you're walking, right? What you'll notice is that as I move my head up and down, right, my hip up and down, my head's going to move up and down, but they're not going to do the same timing. They're not going to both go up and down. That happens with an action figure. When you pick up an action figure and play with it, and it's very rigid and it's not very flexible, it's going to behave differently. So we're trying to show us that things resist movement. They do similar things, but not at the same time. So squirrel's pushing up, tail is down. Now this direction changes. The hip is going down. What direction is the tail going? Going up, okay? And what you'll tend to see is this ripple, right? So if you look at this shape, right? Right? There's a wave rippling through, okay? So that's how you can animate, right? Changes in shape. The two biggest changes in shape you'll see with something curved, something concave, and something convex, right? A big change in shape, graphically going from one shape to another. The computer will give you an in-between like this, right? Which is what makes things look wrong, right? When all of a sudden there's a very abrupt change in shape that doesn't seem to flow. If I connect this, imagine this is the top view, and I'm looking at the hip, and this is the tail, and then I want to go all the way over here. And then how do I figure out how to do the in-betweens? Right? So what you would start looking at is, well, okay, I have an angle here and an angle there. So that means I've rotated this way. That means drag is going to be which direction? If this is the primary force, I mentioned it's the opposite. So this is rotating to the right. What would drag be? Yeah, so it's going to resist, right? Now, the part of the tail that is connected to the hip is going to do exactly the same thing. It doesn't have any flexibility. It's right there. So if I start the tail moving and I say I move this way, so I've moved this, the tip goes here, right? So that's right there, connected right at the base. But what happens here? This is further along, right? All the little pieces of flexibility are going to resist that. So that's going to stay pretty much in the same place. And then what I need to do to connect them is, as you mentioned, an S-curve. The way to get from one shape to another is through S-curves. So how do we start planning something like this? Well, what's important is if you can understand something simple. So in this example here, what is this kind of animation? We did this the first week. Pendulum. Okay. So you're like, oh, I guess it does come in handy, right? Yep, sure does, right? So we can see that we have an extreme over here and an extreme over here. While the character is coming forward, right? So this is the primary direction. You can see that the entire body, you're trying to show people that everything is dragging behind, right? There's a leading edge and everything else is dragging behind, including the tail, right? Everything is resisting that. And then what happens is the hip reaches a maximum. That's as high up as it's going to go. Has the tip of the tail reached the same point yet? No. Okay. So it has this property of matter that's called momentum. Okay. Now if we go back to physics class, okay, momentum equals mass times velocity, right? I got a degree, so I had to learn all this stuff and go through calculus. Many of you might have done the same thing. Now, what's important is not the equation, but what this means, right? Something that's heavy can go very slow and have the same momentum as something that's very light that's going incredibly fast. If this was a metal chain, it probably wouldn't behave the same way as a light, fluffy tail, right? So this is where your observation comes into play. You got to go look at things and say, well, how does a squirrel move? If I don't know how a squirrel moves, there's no way I'm going to be able to animate it. It might feel wrong. But the important thing about momentum is to understand that momentum carries objects through. They can't just reverse on a dime unless they hit something. So the momentum of the hip has reached its maximum and it starts going this way. And the tip of the tail is still going that way. So that's called overlap. Things don't time all exactly at the same moment. When you run, right, and you change direction, your body doesn't all hit the exact same key at the same time. So your body, your legs might be doing more of the work and your body could overlap when you change direction. When you slip and fall, you don't hit the ground all at the same time. You might trip on your feet, then hit with your knees, then land on your tummy, and then your head and your arms follow through. So it doesn't happen all at once, right? There's a cascade of events that usually occur at different times. And this is just observation. If you just look at film frame by frame, you'll notice this. So offsetting timing, right? Making sure that one thing leads and another follows. Studying things like S-curves and how to change from one extreme shape to another. Understanding that the tip of the tail is going to be the last thing to react, but the base of the tail is going to be following the hip, right? So it's going to be doing almost the same thing. They do very similar things, but not at the same time. The tail is basically a pendulum, but it's more complex because the tail's movement is more complex. This is basically a straight line from where you're connected to here. It's pretty much a straight line. It's very simple to understand going forward and back. But the tail, because it's so flexible, behaves differently. Now, no one will notice if the tail is done well. If you've done your job well, this is invisible, right? You will never notice it. You will only notice it when it's wrong. So the important thing is when you're planning this is that nobody would start by animating the tail. I don't think anybody would guess that the first thing you would sit down is draw a tail without a body and try to get the tail right first, and then go animate the squirrel. So because this depends on the character, it depends on these things, right? The whole character. This is usually what's called secondary, right? Secondary animation. So what's primary is the character. Because if the performance gets changed, if a director doesn't like a shot and they want a big change, you got to redo the tail anyway. So this is something you wouldn't draw in a lot of detail. You might just draw, again, a simple gesture, maybe a simple shape to kind of get an idea what's going on. But there's no way you would worry about getting this right or even close until this stuff was done. What you'll soon discover, it's very frustrating to get it right the first time. It does take a lot of guesswork and suffering to get there. There's no easy way to predict how well the overlap's going to go because first you got to do the primary, you got to do the animation, you got to make sure the character's working, then go back and animate the tail. Now in the folder as well, what I've included, there's some other examples here from books that we can look at. And this relates a lot to the whole idea of illusion, right? So here, this image here in Richard Williams' book, the idea of somebody using a fishing pole right in the fishing line, how that would work. But this one in particular, somebody swinging on a rope, right? What you have to imagine is that when you're doing the drawing, when you're posing the character, right, what you have, all we have is a static image. on screen. It does not move, right? That's the most important thing in animation and film, is that nothing moves. It's all a trick. The animation happens between the frames. It happens in your brain, right? The way that your eyes work, right? The persistence of vision. All we have are static images, right? One frame where nothing moves. And that pose has to communicate what's happened. So this pose, right, only works if you are connecting it to a rope that makes it feel like we're going in that direction, right? Because everything is dragging to the left, you assume the character is swinging to the right. If I replaced this pose with this one, they would fight one another. It wouldn't feel like we're swinging in the same direction because the curve and the shape of the body are telling us different things. So if I put this pose in the wrong spot, all of a sudden the illusion is broken. And that can happen quite a lot when you rely on the computer too much, because it will just give you in-betweens, particularly when you're changing direction. When you have an abrupt change in direction or you reach the end point, that's where things get more complicated. Because again, what's going to start moving first? It's not the legs, right? They're going to follow through, they're going to swing through, and as the body goes back, they're going to go like this. So there's lead and follow. It's not going to be a one-to-one, right? Otherwise, things feel very inflexible, very rigid, very mechanical. A horse and a rider. In this case, we've got somebody on the back of the horse, and the horse is kicking like crazy. There's no way you would sit down and animate the rider first, right? Because they're glued to the horse. The horse is the main thing. You got to get the horse right and figure out what that's doing. And again, even though the drawing is very complex, all the anatomy, detail, what you can do is you can distill that down to simple lines of force, right? The first thing an animator should try to animate is not form, but force. Understand the forces at work. Where is something leading? Where is it getting its energy from? What direction is it going, right? Then you worry about the detail. So it's a very important principle. And it also applies to things like camera work. So if you think of like how a camera would move, a camera can have drag, overlap, and follow through too. If you look at how a handheld camera behaves, as opposed to something that's got a very big mechanical rig that's being controlled with a lot of servos or automatic stuff driving it, it still has weight.